Are we all ready to start? It's 1:30. Our first speaker in the second session is Dr. Iwarmura. He graduated the University of Tokyo in nuclear engineering in 1990. He was the winner of the Preparator Award in cold fusion in the year, I think it was 2003 or 4. And he is now working with Mitsubishi, and I think he is absolutely the leader in transmutation through impermeable barriers. So please.
Thank you. Thank you very much. So today I will talk about deuterium permeation induced transmutation experiment using nanostructured palladium calcium oxide multilayer thin film. Okay. This is the contents of my presentation. Firstly, I introduce our method for experiments, and second, we present the results of the batch process experiment. Batch process experiment means, these sections are already presented at the ICCF 17 or 18, and recent consideration taken in this section. And third section, preliminary results on consecutive transmutation experiments. Recently, we are now focused on the consecutive transmutation experiments, and I would like to preliminary results on this experiment. And lastly, I will mention about the replication experiments performed by Toyota Group, Toyota Central R&D Laboratories. Okay. Introduction. Our experimental method is characterized by the D2 gas permeation through nanostructured palladium complex. This is a cross-sectional view of palladium nanosite multilayer thin film. White region corresponds to the calcium oxide, and black corresponds to the palladium. And using this multilayer thin film, we put the elements in advance on this side beforehand, before permeation. For example, cesium or barium, we put on this surface by ion implantation or other method. And then we put this multilayer thin film here, and D2 gas, we fill this region D2 gas. And other side, we kept vacuum condition, and D2 gas dissolve on this surface and permeate through like this. And then we can observe the transmutation reaction on the surface. That's our method. And this figure shows reactions observed in the case of gas permeation. We observe the transmutation reaction of cesium to praseodymium, and strontium to molybdenum, and barium to samarium, and calcium to titanium, and tungsten to platinum or ozimic. And if we summarizing these experimental results, we can see some features for our transmutation, permeation in this transmutation. One is alkali or alkaline metals. Electron emitter elements seems to be very easy to transmute by this method. And second is some rules exist, target element and the product element. In this case, cesium plus 4D get praseodymium, and this case 4D. And the barium case, we need a 6D barium plus 6D get samarium. So we can see some rule, 2D or 4D and 6D difference between target element and the product element. That's the summary of our experimental results. And this figure shows progress in permeation experiments. Before 2010, we performed mainly gas permeation experiments using a vacuum chamber or a very clean environment. We performed this gas permeation method experiment. During this time, our research objective is mainly basic research, mainly what is happening in this system and what factors have an effect on this phenomena. And before 2010, product about the nanogram order, usually nanogram order, we have so much fluctuation but the nanogram order. And after that, from 2011, 2012, we focus on the increase of products for future application. And we used the electrochemical permeation. Using electrochemical permeations, we can get more products about 2 or 3 orders larger than gas permeation method. And then, recently, we are now aiming at consecutive processing. A batch processing, we call that usually before permeation, we put some cesium. In the gas experiment, we put the cesium on the palladium surface. And in the electrochemical permeation case, we put some fixed quantity of cesium, or we put some cesium. But consecutive processing, we are now aiming at consecutive transmutation of cesium using a flowing electrolyte, circulating electrolyte. We are now aiming this kind of process. Okay, so we at first we present the batch process experiment results. Okay, this is a figure for praseodymium dependence on D2 gas pressure. In this case, we focus on this transmutation of cesium to praseodymium. This line means a conversion rate. Conversion rate means how much portion transmuted to praseodymium of cesium. And this axis means the amount of praseodymium, nanogram per square centimeter. And the blue point corresponds to the low pressure. Low pressure means about the 1.2 and 1.3 atoms. And high pressure corresponds to the 1.8 and 2.3 atoms. As you can see, high pressure region have a large amount of praseodymium and a large high conversion rate. So we try to electrochemical permeation method. This figure shows the comparison of gas permeation and electrochemical permeation. In the gas permeation method, D2 gas filled here, and D2 gas dissolved on that surface and permeate through this palladium complex like this. And electrochemical permeation, D2O is dissolved to D2 plus O2, and also D2 dissolved on this surface and permeate. So in this, so they are very essentially the same, but how to make a D2 is different. In this case, D2 gas is filled on the surface, but in this case, D2 gas is produced by electrochemical reaction. Okay. This is a experimental apparatus aiming increase of D density, and aim of the electrochemical permeation is effectively high pressure. We would like to give very effectively high pressure on the surface. So it's an aim of electrochemical permeation. So this is a picture of our experimental apparatus. It's not so large, but this size. And okay, so I will show you the experimental results, example of experimental results. In this case, this is the top view of the palladium sample. This red region corresponds to the D2 gas permeated region, and the other has no D2 gas permeated. And this one is Sims count and the mass number is here. And this is the results of after D2 gas permeation results. And at the corner, we can see cesium 133 has very high peak. And at the center, D2 cesium decrease like this, about 1 order, 2 order decrease, because this. And correspondingly, in the center region, we can see the increase of many masses, about around mass 140. And if we enlarge this spectrum, we can see that the center and corner is here. Only the center, we can see the mass increase 139, 40, and 141, and cerium 142. And this analysis is performed by SIMS, secondary ion mass spectrometry. So we confirmed by the other method, confirmed this method by ICP mass method. We analyze this region, and this region and center and corner region we analyze. And we can see that praseodymium or cerium mass number also increase around here. So SIMS and ICP mass gave similar results. And also we analyzed this sample by XPS, and also we can see that the praseodymium peak, it is not so strong, but it's a praseodymium. So we can see that after permeation, cesium, praseodymium, and other lanthanide element increase in this case. And other, okay, I would like to next point. And I will describe the observation of a gamma ray. So, because we have a large amount of praseodymium or other elements, so we introduced a gamma ray detector near the apparatus. This is a figure of our experimental system. Germanium detector, pure germanium detector is here, and this is the lead shield, and then this is a reactor cell. This is the result, example of gamma ray detection, number E16. This is the time, experimental time, and this one is voltage. We usually, in this case, we firstly start at 3 volt and 4 volt and 5 volt, increase up the voltage, and correspondingly, this is a current. Red one is a current. Current is increase. And also, blue one is pressure. Pressure corresponds to the D2 permeation rate. So at first, we have very small D2 permeation rate, and if we increase up large voltage, we can get a large permeation rate. Then, and in this case, we use the palladium Y203 palladium multilayer thin film. We check that instead of Y203, we get transmutation reactions using this sample. And in this case, we cesium is ion planted like this. And in this case, we use a 0.5 molar cesium NO3 solution. And we divide the period 1 and period 2 and period 3. And the background measurement here and the before measurement, we also measure background. And this is a result example of a gamma ray measurement, period 1. During period 1, we can see the very clear peak, about 609 kilo eV here. But this peak vanished after period 1. But not so clear, but around 511 kilo eV, like an annihilation peak we detect in this case. Also, period 3, we observe the near similar peak. So, in this experiment, period 1, we can see the 609.5 kilo eV gamma ray, and after that, this peak vanished, and this 511 kilo eV gamma ray detected. And in this case, after permeation, we measure the sample. We can see the very clear placidemia peak from E16 sample. And next is the other example, E28. Also, in this case, we started 3 volt and 5 volt is here, and period 1 and period 2, we correct the gamma ray spectrum. And this is the results of period 1 and period 2 and the background spectrum, around 1.2 mega, 100 kilo eV to 16 over kilo eV. So we can see that this black one corresponds to the period 1. The other region, period 1 and period 2, and the background is very similar. But you can see clear gamma ray peak at 1445 kilo eV. And this is a K40 peak, potassium 40 peak. So, and you can see this peak is very clear and stable. So this peak emitted only for period 1 in the same sample. Also, in this period 1, we can see other peak, and this one is 1,748 kilo eV. And other peaks we also detect in this case. And detected gamma rays here. This one and this one I show you. This one and this one I show the spectrum. The other peak, not so strong, but clear peak is here. And we investigate what species can explain this peak, but we cannot explain from the one nuclei, unstable nuclei. we search many database, but we cannot find one species. And also this experiment, we try to replicate this experiment. We tried 2 times, but we could not detect the same gamma ray. So it's very difficult experiment, but this peak is very clear, but the rate is not so high. So maybe this observed gamma ray seems to be attributed to a minor short-lived nuclei. So I would like to continue this gamma ray detection research. Okay, so next point. I would like to a preliminary results on consecutive transmutation experiments. So as I say, usually we put the cesium or other elements beforehand, and on the fixed quantity of cesium here. In this case, saturation of electrolyte, we can provide much cesium on the surface. And this one is a electrolyte, and this is a palladium calcium layer, multilayer thin film. So consecutive transmutation, and we have another aim for this new experiment. This is the figure for the temperature and d by PD relation. In this area, you know very well, I think, at 1 atom. So, and palladium have, if we increase up the temperature, palladium has d by PD goes down. So temperature goes up, d by PD goes down. So in this case, in the batch experiment case, we suppose we suppose that the surface temperature get very high, so we should cooling on the surface by circulation of electrolyte. So we start this kind of experiments. This is the figure of a new experimental apparatus. Pump is here, and the reaction cell is here. And in this Teflon made cell, we have a palladium calcium cathode is here, and platinum anode is here, and the electrolyte is circulating from here and from here, and go out. From inlet is here, outlet is here, and in this case, 0.1 cesium NO3 electrolyte we use, and this is the evacuation rule. This is the summary of reaction rates of batch versus consecutive processing. This one is current density, and this is the reaction rate, microgram per square centimeter per week. This is the result of batch processing using electrochemical permeation here, and consecutive processing, new experiment is here. And you can see that new type of experiments have a higher, obtain a higher reaction rate compared to batch processing. And also, this is the example of the experimental results. Products change. This is a batch, and this is the results of palladium calcium thin film after permeation, and this is the results of a solution, electrolyte, before after permeation. And in the batch case, we can see mainly lanthanide as, in this case, we focus on the lanthan and cerium and praseodymium only. In the case of batch, we can see on the thin film, this one, but in the solution, we have not so much product. But the new experiment, consecutive transmutation experiments, we have limited products on the palladium thin film, but much products in the solution after permeation and circulation. So now it's a preliminary results, but we can see that in the case of batch experiments, products mainly on the palladium thin film, and the consecutive experiment, products is in solution. So anyway, new experiments we got higher reaction rate and products in the solution. So we can recover the product using this type of experiments. So we put the cesium like a radioactivity cesium we put, and we get some products here, but in this case on the surface products. But in this case we can recover, we can get the products from the solution. We are now performing this consecutive processing experiments. Okay. So lastly, I will mention about the replication experiments by Toyota R&D laboratories. This paper published in the Japanese Journal of Applied Physics last autumn, November or maybe October. And their title is Inductively Coupled Plasma Mass Spectrometry Study on the increase in the amount of praseodymium atoms for cesium implanted palladium calcium multilayer complex with deuterium permeation. So they reproduce our results and publish their paper. And their experimental apparatus is here. And they gave the D2 gas flow like this, and they use a very similar multilayer thin film. Of course, they fabricate this thin film. And yeah, this is the results of them. They perform 3 times of a foreground experiment. Cesium, palladium, calcium oxide, palladium with D2 permeation experiment 3 times. And this axis means a praseodymium, and here is the 2.5, 10 to 12 atoms per square centimeter. And it's a foreground experiment. And the other is this region that no permeation results. And in this case, they dissolve total palladium sample. We could not this kind of experiment. We usually dissolve only surface, and they also surface no praseodymium, but they dissolve total sample. But they could not find any amount of praseodymium that can explain this large amount of praseodymium. Okay. So I would like to conclude. Deuterium permeation induced transmutation reaction have been observed in the palladium complexes, which are composed of palladium and calcium oxide thin film and palladium substrate. And second, electrochemical permeation, aiming the increase of the local deuterium density near the surface of palladium made increased transmuted products about 2 or 3 or the larger. And statistically significant gamma rays which have clear energy spectra were detected. At present, we have limited examples. Further study is necessary. I still continue this gamma ray observation. And 4, a preliminary consecutive transmutation experiments gave us higher reaction rates and then batch processing up to now. Much products were recovered in the solutions. Number 5, Toyota R&D laboratory successfully reproduced the permeation-induced transmutation of cesium into praseodymium. Thank you very much.
I believe you said something about the transmutation is different depending on whether you start with D2 gas or D2O.
Slightly different, yeah.
What's different?
Yeah, the gas in the gas experiment we in the case of cesium transmutation we get the praseodymium only like this, but in the electrolyte experiment we also have in this case the praseodymium is not so large, but cerium or lanthanide around here. So in the case of electrolyte is not so clean compared to gas. So maybe hydrogen or the other impurities plays some roles, I presume. But anyway, in this case, so we put the cesium 133. We get this red one is correspond to the product, this region, and also this is a platinum region, and we got the this is the tungsten region, and also we get the platinum here. So in the electrolyte experiment, we observed many types of transmutation reactions. I think. Yeah.
Thank you very much.
Thank you. Okay.
I probably should know this, but have you done many of these experiments with hydrogen gas?
Yes.
Not light hydrogen, not deuterium.
Yeah. Hydrogen gas experiments, we do not have any products.
No product.
No products. But H2O reaction experiments, we are now performing. So, in the case of electrolyte experiments, recent experiment, now underway. Yes.
But in the gas experiments, you got nothing.
Yeah, nothing. Same as Total and the center's data. They also perform the hydrogen gas experiment, but they have no praseodymium. This one, maybe hydrogen. They also, yeah, here.
They got a little bit.
A little bit. Okay.
Nothing would have really surprised.
Okay. So.
See, if the effect is due to the flux,
Mm-hmm.
if you've got a gas source,
Mm-hmm.
your flux is not very large because the pressure is not so high.
Yeah.
If you have an electrochemical
Mm-hmm.
loading,
Mm-hmm.
you can get higher pressure and higher flux.
Yeah.
So do you monitor the flux through the gas output on the other side? Can you compare the difference
Yeah.
in flow rate between gas and electrochemical that way?
That's a good question. But at present, we cannot calibrate. We cannot calibrate in this case. So we cannot exact flow rate in this case. Maybe we have a large amount of D2 fracs, but we cannot show the data.
In ICCF 18, David Kidwell made a fairly remarkable claim that the transmutation products are attributable to environmental contamination. Now, looking at all your data, I find that pretty difficult to believe. But have you prepared any sort of formal rebuttal of that claim, such as re-examining your environment for contaminants, et cetera?
Yeah, we always try to. We have a very much concern about the contamination, especially for Praseodymium. But in this case, Toyota's paper also say we also measure the sample of Praseodymium, palladium sample, but we cannot detect the Praseodymium that can explain our results. That's it. Okay.
I noticed that you're using the secondary ion mass spectrometry,
Mm-hmm.
and are you able to determine your isotopic ratios of the
Yeah.
of your elements, and are you able to see if that's
Yeah. Sometimes we can see isotopic ratio anomaly, but in this case, it is very difficult to say that the isotopic distribution anomaly happen in this case. Okay.
So are you seeing a lot of microfracturing?
Microfracturing
Surface?
on the surface?
Yeah, due to the expansion?
Yeah. After permeation, sometimes we measure the surface by SEM, but in our case, we did not found the microstructure in the case of gas rodding. But the recent results, we did not see the surface. So I can say now that in the gas experiment, yeah.
Can you talk about excess heat?
Oh, excess heat. In these experiments, we did not measure excess heat, but some expectation increase up, temperature rise. We expect some temperature rise, but in this case, at present, we cannot say about the excess heat. Okay.
There was a question regarding the flux, deuterium flux,
Yeah.
through the membrane.
Mm-hmm.
You have vacuum on the other side.
Yes.
When you are increasing the voltage, you are increasing the pressure, you are supposed to increase the
Yeah.
permeation.
Yeah. Yes.
Isn't it affecting the vacuum side so that you can sense an increase in pressure, lower vacuum rate?
So you mean that? Yeah. This one is this is the pressure on the vacuum side. This one pressure. Green, blue is correspond to the pressure, so it corresponds to the flux. That's correct. But your question is what? Please.
What is the vacuum rate on the?
Vacuum rate.
The vacuum.
Vacuum rate is here, about 0.02 Pascal
Okay.
region. Yeah. Sure.
Okay. So you told that using electrolysis, the elements are a little bit different using gas.
Yeah.
You remember we used electrolysis using strontium, and we found 92 a long time before that the new elements don't match your four step, but different 4, 6, 8, etc.
Okay.
So I think such data match very well your.
Yes, yes. I remember that.
But
Okay.
that time nobody can understand why.
Okay.
But with Brisbane, not with.
Okay. Thank you. Okay.
Any more questions? Thank you.
Thank you.